It's not supposed to exist a perfect bubble floating in the chaos of the Milky Way. Scientists are baffled, and the laws of physics may need rewriting. Astronomers have spotted a rare, nearly perfect circle in the Milky Way, a supernova remnant named Helios, meaning perfect in Greek. This name seems strikingly appropriate given the object's flawless symmetry. It was discovered using Australia's ESCAP telescope, short for the Australian Square Kilometre Array Pathfinder, a cutting-edge radio observatory known for its unprecedented ability to map wide regions of the sky with incredible sensitivity and resolution. What makes this discovery extraordinary isn't just the remnant's shape, but how radically it differs from what scientists have come to expect. Most supernova remnants are distorted, fragmented, and chaotic. Helios, by contrast, looks as though it were drawn with a cosmic compass, an almost mathematically perfect sphere suspended in the galaxy. Even stranger, it is only visible in radio wavelengths, showing no trace in X-ray, infrared, or optical light. It's as though the universe chose to whisper this object into existence, rather than shout. Helios was first noticed in May 2023 by astronomer Miroslav Filipovic of Western Sydney University. He was analyzing data from the Evolutionary Map of the Universe, EMU, survey, a large-scale radio mapping project that's part of ESCAP's mission to scan vast swaths of the southern sky. During a routine examination of radio emissions, Filipovic stumbled upon a circular structure so symmetrical that it immediately stood out from everything else in the field. It was soon flagged for deeper analysis and formally cataloged as SNR G305.4. 0.2. Initial measurements indicate that the remnant's diameter lies between 45 and 150 light-years, depending on its exact distance from Earth. That distance is still under debate, with estimates ranging from 2,200 to 7,700 parsecs, roughly 7,000 to 25,000 light-years. The uncertainty is typical for radio-only detections, where the absence of multi-wavelength data limits precise parallax calculations. Still, the consensus among astronomers is clear, regardless of where it sits in the galaxy. Its geometry is stunningly unusual. Why is this so important? Most known supernova remnants have rough, jagged edges shaped by their interaction with surrounding matter. As the shockwave from a stellar explosion tears through space, it crashes into galactic dust, magnetic fields, gas clouds, or remnants of earlier cosmic events, which distort its expansion over time. But Helios defies this norm. Its edges remain smooth, round, and consistent, with no obvious signs of external interference. Some astronomers have even compared it to a textbook illustration, a clean example of what a remnant might look like in the vacuum of deep space. Adding to its mystery is its extremely low surface brightness. Helios emits only in the radio spectrum. There are no accompanying emissions in X-ray, infrared, or visible light, a rarity for supernova remnants. This spectral silence is part of why it remained undetected for so long, even though it may have been hiding in plain sight. ESCAP's ultra-sensitive detectors were essential for revealing this ghostly structure. Given that no historical supernova has been recorded in that region and that the remnant doesn't appear in older surveys, researchers believe this is likely its first confirmed detection. Its faintness and lack of spectral features make it difficult to determine its age and composition, but that ambiguity makes it a scientific anomaly worth deeper exploration. Often, it's these outliers that lead to paradigm shifts in our understanding of the cosmos. So, what could have preserved Helios' stunning shape? One likely answer is its environment. Helios is located just below the crowded galactic plane, in a low-density pocket of space that appears unusually calm. This relative isolation likely played a crucial role in preserving its geometric integrity. With no nearby clouds of gas or debris to warp the blast wave, the explosion's shock front expanded uniformly in all directions, forming the near-perfect sphere we observe today. But this serene setting raises further questions. Why was the explosion itself so faint? Why did it emit only radio waves? One hypothesis is that Helios was the result of a type IAX supernova, a rare subclass of the more commonly known type I supernovae. In this scenario, a white dwarf star in a binary system slowly accretes material from its companion until it reaches a critical threshold, leading to a partial detonation. Unlike typical Type Ia events, which completely destroy the white dwarf, a Type Ia-X explosion is weaker and leaves behind a surviving stellar core, often nicknamed a zombie star. This could explain both the remnant's low brightness and lack of multi-wavelength emission. Type Ia-X events are thought to be more common than we can currently detect, mainly because they're so faint and easily missed. If Helios is indeed the aftermath of such an event, it would represent one of the clearest and cleanest examples of this elusive category yet discovered. Other theories abound. Perhaps the progenitor was a runaway star, ejected from its stellar nursery before exploding in isolation. Another possibility is that a prior supernova cleared the region, creating a clean slate for Helios's perfect expansion. But both ideas carry implications that raise further puzzles. If the remnant is young, why is it so faint? If it's old, how has it maintained such pristine geometry for thousands, or perhaps tens of thousands, of years? And then there's the central mystery. There's no visible compact object, no white dwarf, neutron star, or pulsar at the remnant's center. Without this, it's difficult to trace its origin definitively. Is it hiding in the radio data, too faint to detect? Or was the core ejected, absorbed, or somehow erased? The discovery of Helios has far-reaching implications for our understanding of supernova remnants, especially those residing in less explored regions of the galaxy. For starters, it reinforces the idea that the environment surrounding an explosion plays a critical role in shaping its aftermath. Traditionally, scientists focused on the energy and type of the supernova itself, but Helios suggests that even a relatively low-energy event can create a long-lasting, symmetric remnant if it occurs in a clean, low-interference environment. This has led some astronomers to reconsider the demographics of known supernova remnants. Most previously studied examples come from dense regions near the galactic plane, where interactions with gas and dust are frequent. But what if a whole class of symmetrical, low-emission remnants like Helios exists in off-plane, low-density regions, undetectable by all but the most sensitive radio instruments? Indeed, Helios may be the tip of the iceberg. With the upcoming Square Kilometre Array, SKA, the world's most powerful radio telescope currently under development, we could uncover hundreds or even thousands of similar objects. This could lead to a major revision in our understanding of stellar death, particularly for supernovae that don't fit the chaotic mold. Ongoing studies are already focusing on the southeastern edge of Helios, where a slight radio enhancement has been observed. This may represent the early stages of interaction with surrounding interstellar material. If verified, it could help scientists estimate the expansion velocity and narrow down its age. Meanwhile, astronomers are also scouring the center for any sign of a compact stellar remnant, which would offer crucial clues about the explosion mechanism and progenitor system. Helios proves that not all stellar deaths end in chaos. Sometimes, they end in silence, a whisper rather than a scream. Its quiet, perfect symmetry challenges long-held assumptions about how the universe operates in the aftermath of explosive events. Could it be a rare explosion type, a quiet stellar farewell, or something even more exotic? Whatever the truth, Helios reminds us that the universe still has secrets to reveal. It's often in the unexpected anomalies, the quiet corners, and the barely visible signals that science finds its next breakthroughs. Stay tuned. This is just the beginning. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. Thanks for watching, and we'll see you in the next.